Okay, next video. I'm just going to look at the whole page all at once, so we just finished that one, so we don't need to be seeing it some more. Compare those two problems. Cosine to the fourth x, cosine x to the fourth. And the real point here to these two problems is not the calculus behind them, but the notation, that students mess up the difference in the notation between these two problems quite frequently. And they're completely different problems. This, written this way, means this, cosine x to the fourth. And it will be written, you will see it written both ways. More commonly, it's written this way, but you will see it both ways. And so you have to identify, be comfortable with both notations, and very importantly, since you will see it this way more often, it means cosine x, quantity to the fourth. And so once I see it like this, I've got an inside function of cosine x and an outside function of an exponent of 4. So I start on the outside, multiply by that exponent, decrease the exponent by 1. So derivative outside, and then plug in plane inside. So on the inside just goes my cosine. Again, the most common mistake we get here is people doing the derivative there. But the time for the derivative of the cosine is on the end, that the last part of the chain rule is derivative inside. And so I get 4 cosine x cubed, then the derivative of cosine x is minus sine x, and then final answer, just looks a little prettier to put the negative up front, so negative 4 cosine cubed x sine x. So there's that. Now contrasting that notation, cosine to the fourth x, cosine x to the fourth. It will help if you remember that in normal situations, and this is kind of special here, that's kind of when we're shortcut special notation, but in kind of normal cases, an exponent applies to the one symbol to which it's adjacent. So the only thing that's being raised to the fourth here is just the x. And again, you will see it both ways. And so you've just got to remember that if it's written this way, cosine x to the fourth, it means that only the x is written. Or only the, obviously only the, that was a stupid sentence, the x is written, only the x is written, only the x is being raised to the exponent of 4. So again, really the point to these two problems is they really are very, very, very different problems, and you've got to recognize the difference and understand what they mean. So this one, only the x is being raised to the 4. So I have an inside function of x to the fourth, an outside function of cosine. And remember, a trig function and its argument is never a product. Never. You can always think of a trig function and its argument, a trig function and its angle as a composition. So using the chain rule, I start on the outside, derivative cosine is minus sine, and then angles do not change, arguments do not change, and plus you plug in the plane inside. So there's derivative outside, plug in plane inside, then the rest of the chain rule times the derivative of the inside. Then finishing this guy up, that's going to be negative sine x to the fourth times 4x cubed. And all we can do to simplify this one is, and it isn't any simpler, it's just a little prettier, move the 4x cubed to the front. And so there's my final answer. And again, notice the angle does not change. The angle started out as x to the fourth. Yes, the cosine changed to negative sine due to calculus, but we didn't do any trigonometry. And so my angle stayed the same, still x to the fourth. Okay, moving on a little bit more. Let f of x equal e to the x and g of x equal 5 to the x. Find f of g of x. So f of g of x, written with the little circle, means same thing as nested. Start on the inside. G of x is 5x. F is e to the x. Now replace that x with 5x. And so I've got e to the 5x. And so the point here is that this is a composition. Let's move that up a little bit. So my point here is, so e to the 5x is a composition with 5x being the inside function. That's a composition, which means when I differentiate it, we're going to use a chain rule. And kind of just cutting to the chase here, what the chain rule is going to do for my natural exponential function, that's e to the x, that's the natural exponential function. What the chain rule is going to do, we see right in here, in general, for u equal f of x, the derivative of e to the u is e to the u du dx. And so let's zoom in a little bit so you can see that a little bit better. We're starting to see some what are called, some derivative formulas, and you'll see this a lot when we have derivative formulas. You'll see this u, and that u always represents some sort of function. They just don't want to write down f of x. I guess that's just too much to write down. So whenever you see this sort of thing, e to the u, and later on when we get derivative integral formulas and stuff, that u always represents a function. So what we have here is the derivative of e to the u, where e to the u represents some sort of function, is e to the u times du dx. And that du dx is coming from the chain rule, that we know that the simple derivative of e to the x, the basic derivative of e to the x, is its e to the x. And so I still get that repetition part. The derivative of e to the u is e to the u. But u now isn't a simple plain variable. U, even though it looks simple and plain, what you got to get used to is they always mean, when you see this e to the u and later on other formulas with u in there, u is actually represents a function. And so the chain rule, we get the repeat part, but since it's not a simple plain variable, we get times du dx, or in words, the derivative of the natural exponential function consists of the function times the derivative of the exponent, or right here, repeats times the derivative of the exponent. That's how you will always be able to differentiate the natural exponential function. It repeats times the derivative of the exponent. And we get that derivative of the exponent from the chain rule. And that will always work. Even if it's just e to the x, you were just told to believe that the derivative of e to the x is e to the x, which it is, but these words would still work. Repeats. So if we're talking about e to the x, and we say repeats, well, e to the x times the derivative of the exponent, well, if the exponent's just 1, times 1. So you'd have e to the x times 1, which is the e to the x. So these words will always describe how to differentiate the natural exponential. So doing this guy, go for the words. They're the easiest. Repeats. Derivative of the exponent. And so 5e to the 5x. Repeats, derivative of the exponent. We'll do it every time. There we go. Next one. Okay, they're going to make them just a tad harder. So again, I got a composition. My inside function is e to the cotangent 3x. My outside is the secant. So we're going to start on the outside. Derivative of secant is secant tangent. Left myself lots of room. Now remember what the words are as far as the chain rule goes. That this is derivative outside, plug in plane inside. Which means in each case, what I'm going to put in those parentheses is e to the cotangent 3x. And that also corresponds with that my angles do not change, my arguments do not change. So since my original argument was e to the cotangent 3x of my secant, for my secant tangent, it's still cotangent 3x. Then the rest of the chain rule times the derivative of the inside. And so there's derivative inside. Okay, so we are done with this first part, so I'll just write it down again. Then I get to the end there, and I use my words for e, which is it repeats, and then we'll do symbols and get the next, do the actual derivative on the next step. Repeats, derivative exponent. Okay, continuing to whack away on this problem. I'm done with all this first stuff. So I'll write it down again. Then I get to the cotangent. We can do the derivative with the chain rule, or we can remember that the effect of that 3 from the chain rule will be to multiply it. That when you're doing your trig functions, if your argument is linear, mx plus b, the chain rule is going to give us that the effect of that 3 is to multiply by it. So I can just write down that 3. Then the derivative of cotangent is negative cosecant squared. The angle does not change. And there's my derivative, and nothing really simplifies here. The most you would maybe want to do is put that negative 3 up to the front. But nothing else significantly simplifies here. There's my answer. Okay, let's end that video.